Hi all, today we discuss examples of vector space. Okay. First, our set S is set of all x. The matrix XYZ belongs to R3. R3 means R cross R cross R. Consider this element as an element of R3 such that y equal to 0. Okay, we need to verify whether this is vector space or not. With respect to the operation, uh, u, if you take u belongs to u and v belongs to s, then u takes the form a0 b and v takes the form c0 d. Then define the vector addition u plus v as a plus c 0 b plus d. If this is the vector addition, and the corresponding scalar multiplication is alpha times u is alpha into a0 b, that is equal to alpha a 0 alpha. Suppose this is the these are the vector addition and scalar multiplication of multiplication defined on S. We need to verify whether this S is a vector space over reals. Okay. If the underlying field is not specified, we need to take F as R. Okay. That means these alpha, beta, gamma comes from this R set of all reals. Okay, so we need to verify 10 axiom. That is the thing we need to remember in order to verify the conditions of a vector space. We need to start with a set and a set of scalars and two operations. One is vector addition and the second is scalar multiplication. Okay, so we are set with all these four quantities. Then we need to verify 10 axioms. Okay. So A1, what is A1? A1 is defined as the closure property. If you take any two element A0, B as U plus B, C, 0, D, then you can get the same thing, A plus C, 0, B plus D. Obviously, this is an element of R3 with a middle term is 0. That is the requirement of being an element of this S. Okay, so we need to prove that this is always, we have shown that this is an element of S. Similarly, this is also an element of S, since these are real numbers with the middle term is 0. Okay, so we verified S1 and A1 simultaneously. Okay, that is obtained from the definition itself. Next, we need to verify the commutative property. What is commutativity? U plus V should be same as V plus U. Okay, so that is very true from this definition itself, because A plus C is equal to C plus A, B plus D is equal to D plus B. So this is also true. So A2 is verified. Okay, then for A3 we can say that associativity, if you have U, V and W, U, V and W, we need to associate the last two ones, and we can take those elements as PQR. So A0B plus the first V is taken as C0D, and finally W is taken as P0Q. Okay, when you add all this, you can get A plus C plus P, 0, B plus D plus Q. We know that all these quantities are real numbers. You can associate in any manner. A plus C plus P is same as this one. B plus D plus Q is same as this quantity. So associativity is there. So this shows that A3 is also true. Clearly, 0 0 0 is an element of, this is an element of R3 with the property that u plus 0 is same as 0 plus u, that is same as u. Okay, here you can verify the you can use the commutativity, because these all are vectors, so you can easily write in any manner. Okay, so this shows that a4 is verified. Okay, for f5 corresponding to u, use a0 b, you define minus u, or you can collect minus u from s such that minus a0 minus b. Obviously this is an element of R3, since a and b are real numbers, minus a minus b are also real numbers. So this shows that a5 is true. Okay, so we have verified a1 here, this is a1, and a2, a3, a4, a5. Now there remain 5 more axioms. Among them, one is verified as well. That is nothing but this closure property of scalar multiplication. That is also true. Now what is S2? S2 is nothing but alpha dot beta dot u. Okay, if you take any alpha dot beta dot u. Okay, so this is nothing but alpha into beta a 0 beta b. So this is equal to alpha beta a 0 alpha beta b. Since these are all real numbers, we can associate in any manner. So this shows that S2 is also true. Okay. For S3, we can take U as, or if you consider 1 into A0B, you will get A0B. Okay. So this shows that S3. Okay. Now there remains exactly 2. That is alpha plus beta times A0B. So this is equal to alpha plus beta times A0 alpha plus beta times B. Okay, so this can be written as alpha times A plus beta times A. This can be written as alpha times B plus beta times B. Okay, so from this you can write it as alpha A 0 alpha B plus alpha times beta times A0 beta times B. Okay, this proves S4. This is the fourth axiom corresponding to the scalar multiplication. Now we need to verify one more axioms called alpha into u plus v. So that is alpha into A0B plus C0D. Okay, we need to multiply this. That is same as alpha times, when you add all this, you can get A plus C 0 B plus D. From this you can write alpha into A plus C 0 alpha into B plus D. Okay, so this shows that S5 is also true, because you can, these are all real numbers, you can easily distribute this alpha to A plus C, that is alpha A plus alpha C, similarly alpha B plus alpha D. Then you can retrace the procedure, or you can split again these as two matrices, and you can easily verify this S5. So this is the way we verify the 10 axioms to prove a setting is a vector space. So this is very lengthy procedure. Even though it is very simple, it takes time for verifying all these 10 axioms. So next our intention is to develop a theorem, or to propose a theorem which shows a comparatively a smaller definition, or a smaller characterization for this these axioms. Okay, that is our next intention. So in our textbook there are many more examples and non-examples for this vector space. You need to go through all this, and all are worked out problems. So you try to solve all those problems, and if we have schedule a Google Meet, we can discuss those worked out problems in the live interaction. Now we can discuss the theorems on these vector spaces. Okay, that's our next class. So next video onwards we will discuss theorems on vector spaces.